Uh, UVM acceleration using hardware emulator at pre-silicon stage. Abstract. Since the complexity of mobile SoC is increasing significantly, simulation-only based verification can't achieve a higher quality verification for a given time. In this study, enabling UVM acceleration environment where the simulation is accelerated at the pre-silicon stage is discussed. To maximize the hardware resource use and increase the speedup, the acceleration candidate are identified through the simulation profiling. In addition, by introducing a dual domain framework, the existing UVM environment can be used in the hardware acceleration. An automation flow is also that they eliminate the unnecessary debugging and iteration caused by the OOMR out of module reference signals. As a result, the speedup of 17 to 21 times is achieved. The introduction. The complexity of SoC platforms, including both hardware and software, significantly increases since more features and performance are required to process recent mobile applications. It requires more development TAT turnaround time and product cost. However, in order to achieve time to market, the development period stays the same or even less. The verification TAT also needs to be shortened. The current SoC design verification uses UVM, Universal Verification Methodology, simulation environment. While each simulation environment can be developed rapidly, its simulation runtime is slow at the SoC level. In comparison, the emulation is 10 times to 100 times faster than the simulation. Also, the performance degradation in emulation for a large design size is not so high. However, it's not efficient to use the existing UVM-based simulation environment to take advantage of the high emulation speed. Thus, the verification methodology utilizing and improving the existing UVM simulation environment in a hardware emulator is proposed. Both performance enhanced by the hardware emulator and the reuse of the simulation environment are achieved. In this study, the challenge to create UVM acceleration environment at the pre-silicon stage are discussed first. Section 2 describes the simulation profiling result splitting simulation tasks and hardware tasks. In Section 3, the flow to build UVMA environment is focused. I discussed the result on a CPU core emulation and the power-aware emulation with the UPF, Unified Power Format, and SoC are described in Section 4. The simulation profiling. Basically, the DUT, design under test, reside in the hardware. Operations on the DUT would be much faster than the software simulation. However, since all the test vectors used in the existing UVM environment cannot be executed in the hardware, some of them are divided into hardware part and some of them are divided into software part. In this case, if the proportion of the hardware side and the total test time is not large, the emulator cannot be used effectively because there is a little room for acceleration using the actual emulator. In addition, the number of simulation vectors for design verification is very large in thousands of units, but the hardware emulator resources are very limited due to its cost, and it is difficult to perform a large number of simulation vectors at the same time. Therefore, in order to maximize the return to the investment ROI of the emulator, it is necessary to select the test vectors that can have a great effect on the acceleration and use the emulator preferentially. Intuitively, it is clear that the acceleration effect of the test vectors that operate only in the hardware part will be greatest because there is almost no interruption from the software part. The more communication there is, the more overhead will occur and the performance will be degraded. However, it's very inefficient to analyze the source code of all vectors in order to understand the properties of the vectors. So the profiling tool provided by the simulator can be used to figure out which vectors will have a great effect on the emulator. The Figure 1, Simulation Profiling and Acceleration Estimation. A is hit ratio distribution comparison between CPU vector L4 and non-CPU vectors L2. And B is acceleration time estimation. Okay. The figure 1 show the hit ratio profiling the result for the CPU operation-oriented vector L4 and the CPU-free vectors L2 at the simulation stage. The hit ratio is a concept that shows the percentage of the signal toggle that occurs when the test vector is executed. The upper blue part of the graph is expected to be executed in the hardware part, and the large green part is expected to be executed in the software part. As predicted earlier, 99.453% of the hits are expected to occur in the hardware part because there is not much communication with TB in the L4 test based on CPU operation. On the other hand, L2 vector for general IP verification vector with no CPU has relatively large amount of communication with TB. So the hardware part count for about 94%. Therefore, it can be that it is more efficient to accelerate L4 test vectors that have more than a 99% operation in the hardware part. Figure 1b shows how much acceleration will be achieved for L4 cases where more than a 99% hit occurs in the hardware part, because 99.53% of the vector execution under simulation environment can be executed in the hardware part under emulation environment. Execution time will sure be saved. However, communication override between the hardware part and the software part should be considered. Therefore, the acceleration time should be calculated considering software part execution time, hardware part execution time, and communication execution time. The 3. UVMA acceleration environment. A. Dual domain framework. The conventional verification environment generally consists of a single top that have both sensitizable and non-sensitizable component. DUT and the UVM component including UVM driver, monitor, and the sequencer are instantiated in or together. But traditional single TB test bench should be divided into two parts: HVL, Hardware Verification Language Domain, and HDL, Hardware Description Language Domain, to be able to use hardware emulator. Figure 2, Dual Domain Framework. However, there is a limitation in using this structure. As mentioned in the previous section, minimizing the communicative overhead between the HDL domain and the HVL domain and HDL domain can be increase the effect of the hardware acceleration. If the TV vectors are created with this consideration, the result could be slower than a simulation. This is illustrated by an example of the PPMU Platform Performance Monitoring Unit responsible for performance analysis within the SoC. The Figure 3 PPMU Platform Performance Monitor Unit monitor and interface in the UVM simulation environment, TOP, UVM environment, PPMU monitor, PPMU interface, and DUT. Figure 3 shows the UVM simulation environment composed of one top, which is expressed in the monitor part of the PPMU, and the PPMU monitors total the number of AR valid and or AR ready signals in the RD_REQ_CNT in the PPMU monitor through the interface to the PPMU block. To do this, the AR valid and AR ready signals are checked every clock cycle of the PPMU_ interface. This structure has no problem in the simulation environment, but however, it can cause serious performance degradation in the UVM environment separated by HVL_top and HDL_top. 자, Figure 4, PPMU monitor and interface in UVMA environment. Top. Fourth top, HVL top and HDL top. Figure 4 shows the PPMU monitor and interface when configured as dual domain for UVMA in the single top environment in Figure 3. Oh, sorry. The environment Figure 3. If the A clock of the PPMU_ interface is used to add REQCNT in the monitor, even between event monitor, an event between HVL top and HDL top should occur whenever A clock is toggled. So serious performance degradation may occur. Therefore, the part checking the REQCNT is moved to the PPMU interface to be calculated in HDL top. In the PPMU monitor of the HDL top and the REQCNT in the PPMU interface is changed to be used only when needed later. This allows the same function to be performed without degrading the performance of the hardware emulator. At this time, because REQCNT used the HVL top is located on the HDL top side, it must be registered as an export signals on the HDL top side to be accessed from the PPMU monitor over HVL top. The B is a simulation acceleration flow. Figure 5 is a running flow of the UVM acceleration. Figure 5 shows the concept of the simulation acceleration with the hardware emulator. The right part of the picture means the hardware side including DUT and interfaces. The left part describes the software side consists of a test bench, software imaging of DUT and DPIC interface. Each number in Figure 5 will represent a running flow of the simulation acceleration. The explanation of each number is as follows. As the pure simulation, start from 0 time to own software side first. 2 is run on the software side and execute the swap command to transfer control to the hardware side. And 3 is on the hardware side, the vector for the design of the DUT is performed. If the delay of TB is expired during the vector execution, or call is made on the TB side, hardware-software sync process is performed and control is transferred to a software side. Execute the vector statement described in TB, and 6 is when the TB statement is finished, control is transferred to the hardware side again. This process is repeated until the simulation is finished on the software side. At this time, the signal area between the HDL and the HVL and the HDL is called OOMR out of the module reference, and the access permission must be grasped from the HDL side of the TB access to access the corresponding signal. This is discussed in the OOMR signal handling section below. OOMR out of a module reference. Signal handling. Figure 6. Current manual OOMR insertion flow. The figure 6 shows the current UVM environment construction process. After analyzing the files to be included in the HDL side, and the compile process for the hardware side is performed. At this time, the information about the signals accessed from the TV should be specified as well. The OOMR information is analyzed by reviewing the contents of the TV and entered annually to process with the build. After completing the hardware compilation, we proceed to elaboration on the software side. When the image is generated, the test vector is executed to verify the desired function. However, the test vector is sometimes performed well and sometimes drop at a specific point. In order to find the points where the vector stops, it is necessary to generate waveform and debugging for a long time. In many cases, the problem occurs because the OOMR signal is not added. The found OOMR signal should be added to the OOMR information list, and the hardware side compilation step is repeated from this step. If we are lucky, we can get the result of the test vector through only one iteration, but we may need to repeat building process several times because it is sometimes difficult to extract all OOMR signals at one time. So the figure 7 frozen test vector caused by missing export signals. Figure 7 illustrated the problem that occurs the OOMR is not included in the exposed signal list. The OPO output PUR power REQ request signal is included in the OOMR signal list, while OPWR ECH signal and the OPWR up signals are included in the list because they cannot be detected in the UVMA environment migration. If we build the emulator image using the incomplete signals list and run a test vector on image, it will work well to wait statement of OPWR REQ signal, but it will not proceed any longer waiting for OPWR signal, echo signal. So we have to create a waveform and debug the problem. Furthermore, dumping a waveform in the emulator takes much longer than under simulation. This means that we have to devote much time to debugging job that we do not have to, which ultimately reduced the efficiency of UVMA. Figure 8 proposes automatic OOMR insertion flow. The figure 8 shows how to solve the inconvenience of the manual entering the OOMR information. This basic build flow is similar as the shown in the figure 6, but it focuses on automatically entering OOMR information to eliminate the iteration due to missing information. To extract full OOMR information, hardware compilation and software elaboration should be performed once. Once executed, there would be no missed signals. There would be no missed signal because the build software outputs the OOMR information used in the test vector to be in the tool. The generated OOMR information is automatically used as input to the second image build, and we can get the desired result with a single iteration. An image build process is required once unconditionally, but this methodology is useful because we can focus on the original test vector, reducing unnecessary work looking for missing signals. Design library handling. The synthesizable model of a design library can be generally created from the Liberty file. IEEE standard contains PVT characterization, input and output characterization, timing, power, and so on, etc. But the liberty file of the specific design library can be invalid at the early stage, so synthesizable model cannot be created. In this case, the synthesizable model should be generated manually, and this job was one of the main reasons which disturbed flow automation. So we decided not to make the custom synthesizable model when the liberty file is absent. Instead, we use the simulation model which can be executed at the host machine. Then we can build up the automation flow without any compilation error and can learn the compile immediately on the hardware emulator. Of course, the emulation performance can be degraded when the simulation model is used on the host machine due to the communication overhead between the emulator and the host machine. But overall performance doesn't slow down and much because these kinds of models are not used so much at the early stage. The power-aware emulation step. Power-aware emulation step. In general, when configuring an image to use a hardware emulator, not all RTL blocks of the SoC are included. This is the price of the hardware emulator is expensive and the resources must be divided and used by many people. The image must be created using only necessary SoC. Moreover, because the emulator compilation time compared to the simulation, compile time is 2 to 3 times longer. Eliminating unnecessary blocks can sometimes be a useful technique. Power-aware emulation can be performed with the UPF as a simulator does. But the compilation errors can occur due to the information mismatch between the RTL and the UPF, when some RTL blocks are stubbed out because of the machine resources or compilation time. The compilation tool should handle the UPF information at the black boxes without errors. DFS, Dynamic Frequency Scaling Emulation Setup. In general, necessary clocks to SoC are directly forced output port of the PLL on the emulator to execute the DFS test vectors. Many numbers of the clock resources are required. If all clock instances are created at the top in advance, emulator performance is degraded. So only one clock instance should be created in advance, and clock frequency according to the parameters of the PLL should be defined as local parameters. Then we can assign local parameters according to the parameters to the clock instance without a performance degradation. 4 experimental result. We performed our experiment using our mobile AP application process according to the proposed flow. We chose CPU operation-oriented test scenarios because those kinds of tests usually take a long time and have less interruption from test bench. The total number of the scenario is 1 in 37, including the 16 power-aware simulation, and all tests are executed in the hardware emulator without any modification. Table 1 shows the simulation time, emulation time, and speed factor of the normal scenarios and power-aware scenarios, respectively. Table 1. The result of UVM acceleration CPU block. According to the result, the speedup of normal tests is 17 times, and the that of power-aware test is 21 times. This score is quite impressive, but the speedup rates are not so high than expected. The reason is the region is thought to be the design size of a mobile AP used in this test and the simulation time of the vectors. The size of a mobile AP used in this test is about 100 mega gate count, and the simulation performance is relatively fast. So the average simulation time and the average power aware simulation time are just about 2 hours and 5 hours respectively. Therefore, this result cannot show the advantage of a hardware emulator fully. The effect of the speedup will be remarkable when we use large size mobile AP over 1000 mega gate count, which has very slow simulation time, such as over several days. Okay, the 5 conclusion and future work. And in this research, we described how to deal with the difficulties occurred when we are trying to make UVM acceleration environment in the free silicon stage. First, we measured the potential acceleration of the test vector through the simulation profiling to efficiently use the limited hardware resources. Based on the result, the priority of the test vector to perform the hardware acceleration was selected. Second, unlike the simulation, where everything is done on the host machine, the UVM acceleration environment is made up of the HDL domain and the HDL domain, HVL domain and HDL domain. Since the communication and synchronization between the HVL and HDL are the main factors of the performance degradation of this emulator, we moved the clock-related cause of the HVL domain to the HDL domain. Thus, third, we examined the HDL domain should be given access permission to the OOMR signals between the HVL domain and the HDL domain, since the iteration may have a series of adverse effect on the schedule. We propose a flow of adding OOMR with only one iteration by automating the task that eliminates exhausting iteration. Finally, we used non-synthesizable simulation model for valid liberty file and set up power-aware emulation and DFS emulation. According to the pilot test result, we can get about 17 to 21 times the speed up comparing pure simulation time with any test vector modification, even though the speedup result is lower than expected. We can estimate the result of large AP will be better. Okay, thank you. Thank you for your time. I read the UVM acceleration using hardware emulator as pre-silicon stage. Thank you for your time. I'll see you next time. Thank you again.